Good afternoon. Mic again not working. I sent them an email. I even called them, and they are someone will be around to come and fix it when I'm teaching. I say that's fine. Just come, okay? Or if not, you guys will get a discount from that department, right? So we are going to do another example of eccentric buckling. And then we are going to go into design of structured steel columns on allowable stress design, or based on allowable stress design. Now, for this case, I think the example we're going to do is based on centric buckling. Okay, so I've posted this question on Avenue to Learn. If you all can look at this example, let me zoom this out. And there are a few information that we need. Back to the first page. And then I need this table. Right. As you can see, we have an axial load of magnitude 175 kilonewton. So before we do anything, we look at our transformation. So our transformation is given based on the loading. So this is our X. This will be our Y. And over here, this is our Z. Okay, I have not a clue. Have I started recording? I did. So we know that we have a Py, which is equal to 175 times 10 to the power 3 Newton. And I applied parallel to the geometric axis of W250 by 44.8 columns steel, rolled steel column AB, and intersect the axis at a distance E is equal to 12 millimeters. So you look at the distance E over here, you can see that there is an offset. Okay. Knowing that stress yield is 250 megapascal, so we are given stress yield is equal to 250 times 10 to the power 6 Pascal. And then we have a Young's modulus that is equal to 20 times 10 to the power 9 Pascal. Determine the factor of safety with respect to the yielding. Okay. Now, a question like this, if it's accompanied by a table or a graph like this, okay. So I want to introduce you to this graph and where this graph is formed. But before I write where this graph is from, we are going to look at eccentric. Okay, we are going to look at the formula for eccentric loading, and we know that stress max for buckling. We know that stress max is equal to P over A. Now this formula will be given in your term test. Okay, I repeat again. This formula will be given in your term test. So we have this expression over here. 1 plus by EC over R squared. Then we have secant. Then we have half L over R and square root P over EA. Okay. Now, if you look at this table over here, okay, you look at this table. This table is drawn from Euler's equation. Okay, so over here, this is also known as Euler's equation. For eccentric loading. Okay. So this graph over here has a lot of terms that's related to stress max. Okay. So you can see that this is L over R. Another thing you can see that we have our P over A. And another thing you can observe is we have our EC over R squared. So the individual EC over R squared, you can have 1, 0.8, 0.6, 0.4, 0.2, 0.1, and 0. Right? EC over R squared is equal to 0. What does it mean? Anyone? Yeah. Where are you? What do you say? Yeah. So this EC over R squared, this line represents centric buckling. When it's equal to what? 0. For our case, it will never be equal to 0. Are we clear? Okay. So if you plot what you do, if you use Excel to plot this expression, you will get a graph exactly like this. Okay. So when do you use a graph like this? If I provide the graph in the term test, you will use it. If it's not provided, what do? You use the other method. Are we clear? Okay, if I provide this graph in your term test, okay, since all of you are still learning, I will tell you what to do. Is that fair or no? Okay, so I'll tell you if the graph is given, okay, use the graph. If not, don't put up your hand, Eugene, I need the graph, and get any. Are we clear? Okay, right. So this is an easier technique, or if you see what I'm going to do, this is an easier method or quicker. I hope it's a quicker method to determine factor of safety, right? So now, have you all used, are you all learning thermodynamics now? Yes? Are you all using steam tables? Have heard about steam tables or not yet? Some of you, yes, some of you not yet. It's okay, okay? So this is very similar to steam table, but in a graphical form. I'll explain later, right? So now what is given to us? We have a lot of hundreds and the steel and the geometry that we're going to use is the W250 44.8. Okay, so we have to focus on the W250 44.8. Okay. So now, looking at this structure, right, we know that both ends, the structure, are pinned at both ends. Okay, I repeat again, the structure are pinned at both ends because over here, M is equal to 0 at the top, at the bottom, M is equal to 0. How many of you are satisfied with that answer? None of you are. So if we were to go back week 3, or someone told me it's on Wednesday, right? Can you all tell me, or on Tuesday? Okay. If you look at this, right? If you look at this now, right? The structure is pinned at both ends. Because moment over here is equal to 0, moment over here is equal to 0. And if we were to draw the free body diagram, we have a reaction. We will have a reaction force at the bottom, and we also have one at the top in a linear direction. Yes or no? When that's the case, it's very similar to this, except we have an extra moment due to the eccentric loading. So now this is, and moment is equal to 0. As I said, this is, for this case, we did not consider the eccentric loading yet. Okay, we did not consider the eccentric loading yet. Okay, so now, so when we were to find the equivalent length, take it like a centric loading. Repeat again, if you want to determine the equivalent length, take it like the fixturing is what? Centric loading. Okay, I put down here to determine the equivalent length analyze the fixturing based on centric loading. Okay, I know there'll be some smart one telling me, Eugene, that's BS because there's a what? There's a counter moment. Fixturing will not have a counter moment because it's pinned at what? Both ends. Are we clear? Okay. Right. So now we are going to expand this table. Now, when we expand this table, we have to be very, very careful. Okay. Again, a lot of students make this mistake unconsciously. So what mistake do we usually make? Okay. Now, if we look at this transformation, okay, so this diagram over here, we are going to follow this transformation. Okay, we're going to follow this transformation. So this will be our X, this will be our Y, and this will be our Z. Okay. So if we were to look at this diagram over here, I'm going to zoom in over here. Okay. X is, yes. Moment is equal to 0. The force are acting in one direction only, and it's a point load. We assume it when we look at the fixturing, we only consider the centric loading because there's no equivalent length given to us in eccentric loading. Daniel, it's pinned because there's no counter moment. You say okay out of fear, or you say okay because you understand? Okay, sorry, okay, don't be fearful. I do apologize, okay? So it's just pin. It's just, you see only there's a reaction force, there's just what? Pin. Okay? Right? There's no counter moment. Right? Come back to here again. Okay, I'm going to slow down a lot. Okay, I'm not going to finish this question. I'm going to answer all your questions. Wait, Daniel, you get it? Because there's a coupled load below and there's a coupled load on top. There's no counter moment. They were not, it is not sure that it's fixed on one end. Wait, yes or no? Can you see this diagram down here? Can you